Today we'll talk about inverses of functions. The inverse of a function is created by interchanging the domain in the range or the x and the y value. Also, we know that a graph of a function and its inverse are reflections across the line y equals x. In this example, we're going to find the inverse of the function y equals 3x minus 5. So the first thing we'll do is write the linear function, and we're going to switch the x and y variables. Now we are going to start to solve for y, and when we're finished, we get the inverse is y equals x plus 5 divided by 3. If we were to look at this graph, we can see that the two inverses are reflected across the orange line, y equals x. The darker green line is the original function y equals 3x minus 5. The aqua line is the inverse, y equals x plus 5 divided by 3. We can see that the inverse is also a linear function. So we can rewrite these by removing the y's and naming them both as functions. F of x is the original function and it's equal to 3x minus 5. And the inverse is denoted as f of negative 1, which means the inverse of the function of x. We also remember that the x and y values will be interchanged between the function and its inverse. In the function, we can see that the point 2 comma negative 1 exists, and when we interchange those x and y values, we can see that in the inverse, the point 1 comma 2 is also in existence. If we would like to verify or prove that these two functions are indeed inverses, we must prove that the composition of each one with the other is equal to x. So we'll start with the function, and we'll find f of the inverse of f, and we're going to show that it's equal to x. So when we set it up, we're going to have the original function 3x minus 5 will have x removed, and the inverse 1/3 x plus 5/3 will be replaced there. When we distribute the 3, we get x plus 5 minus 5, which indeed is equal to x. But we can't stop there. We must, in order to prove or verify, we must also show that the opposite is true. So when we start, we're going to set up the inverse function 1/3 x plus 5/3 and replace the x with the original function 3x minus 5. After distributing, we get x minus 5/3 plus 5/3 is also equal to x. And this is the way that we will prove that two functions are inverses of one another. For a moment, I'd like to think about the inverse of the function of x, where y is equal to x squared, denoted by the darker green parabola. We still have the orange line of reflection, y equals x, and the aqua parabola has been reflected over this line and represents the equation x is equal to y squared. We can see that the inverse is not a function in this case, so we must restrict both the domain and the range. If we take away all negative values of x, the left half of the parabola would not be there. And then when we reflected it, the bottom half of the inverse parabola would not be there. And we would have functions for both our original function, our original equation, and our inverse of that. This graph would look more like this, where both curves are now in quadrant 1. We've restricted the domain to positive numbers and 0 and graphed them together in quadrant 1. In order to find the inverse, we're going to replace the original function name f of x with y equals x squared. We're going to switch x and y and solve for y by taking the square root. Normally, the square root would have a positive and a negative value. However, in this case, we're going to choose only the positive value because of the fact that we have restricted our domain. We can also see that this function in reverse and its inverse share points where the x and y coordinates have been interchanged. In the original function, the point 2, 4 exists, and we would expect then that in the inverse, the point 4, 2 would also exist, and it does. What we can see then from this example is that the inverse of a function f is also a function if and only if no horizontal line intersects the graph of f more than once. And so we can apply the horizontal line test to the original function. In the case of y equals x squared, if we apply the horizontal line rule, we can see that the horizontal line does, in fact, intersect the parabola more than once, so that when it would be reflected and the parabola would be centered along the x-axis instead of the y-axis, that horizontal line would then be a vertical line, and it would fail the test for function. However, in a cubic function, such as y equals x to the third, this function does pass the horizontal line test. Suppose we have the function 2x cubed plus 1, and we'd like to determine whether the inverse of the f is the function, and then find the inverse if it does exist. So we can see that the graph would be translated up by a unit and stretched by a factor of 2. We can make a rough graph and apply the horizontal line test, see that it does pass, so the function must exist. So we're going to write the original function. We're going to replace x and y with each other and start to solve for x by subtracting 1, dividing by 2, and taking the cube root of both sides. When we get this inverse equation, we can graph it. We see the orange line here is the reflection line, which is y equals x. The darker green is the original cubic function, and the aqua happens to be the reflection or the inverse curve. Once again, we can see if their ordered pairs actually have their x and y coordinates reversed. In this particular function, 1, 3 exists on this particular curve, and on the inverse of the curve, the point 3, 1 also exists.